Okay. Hello, guys. Good morning. It's my pleasure to introduce our speaker today, which is Krandel, who's going to talk about uniformly distributed measures.
All right, thanks so much. Yeah, I'm really honored to have the opportunity to talk to you guys today. So yeah, with that, I guess we'll get right into it. The talk is about uniformly distributed measures in Rn. So I think the best way to begin is really just with a definition, right, to tell you what that means. So on the top here, I wrote, so a radon measure mu in Rn is uniformly distributed if there exists this non-decreasing function I call f sub mu from r plus to r plus, such that the measure of a ball of radius r is equal to this function evaluated at r. This is for all x in the support of my measure mu. Okay, so, and I wrote the definition of the support here to the right, in case you forget, is just the set of points where the measure of every ball around that point is greater than 0. Okay, so, what does this definition mean? Really, it just means that the measure of a ball of radius r for fixed r is independent of the point I choose. Right, so for every point in the support, I just have the same measure for a ball of radius r.
Could you remind me what radon measure is again?
Yeah, really the specific properties of radon measures aren't actually very important. Really, you just need to know that it's their balls are finite, and radon measures are.
Could I just
they're
pretend
nice
it's a big measure?
Yeah, you can really just pretend that it's a Lebesgue measure, basically. Yeah, so this is the definition of a uniformly distributed measure, and then basically the point of the talk is going to be to show how this, this one simple condition actually imposes pretty strong constraints on the form of my measure mu. Okay, and so here I've written a little outline of what we're going to see. So first, I'm just going to give you a bunch of examples. So like Ben actually just mentioned, the simplest example is just Lebesgue measure in Rn. It's one that we're all very familiar with. I'll give you a sort of a variety of examples which tell you the different sort of flavors of measures that are in this class. Then secondly, I'm just going to derive some properties of mu, prove some lemmas, and then I'll get to two sort of really interesting results about the constraints that this condition imposes. I'll prove B here that the support of mu actually has to be a real analytic variety. And then after that, I'll prove that in the case of compact support, support of mu actually has to be a real algebraic variety. Okay, and we'll actually be able to write down polynomials with coefficients in terms of mu that the support of mu will end up being the 0 set of. Okay, and then after that, if we have time, maybe I can give you some idea of how these results actually give classification results for these measures, at least in R, and a partial classification, the classification in the case of compact support, really, in the plane. Okay, so that's the plan. Okay, and by the way, feel free to interrupt me at any time to ask questions if I write something that's unclear. Okay. Okay, so with that, let's get into some examples. So, right, so number one, right, actually we already talked about this, right, is just ln and Rn, which is just Lebesgue measure in Rn. Right, so for this guy, what's this distribution function, this f mu, fln of R, just Lebesgue measure of a point, or of a ball of radius r, is what I'll write omega n times r to the n, right, where omega n is this dimensional constant. Right, so this is, this distribution measure is proportional to r to the n here. Okay, so that's pretty simple. Secondly, I'll write here mu is what's called H2 on S2. Okay, so when I write S2, I mean, this picture I've drawn to the right is just the sphere embedded in R3. And so what is this H2 thing? It's a measure, it's called Hausdorff, or two-dimensional Hausdorff measure. Really all you need to know is that H2 measures the area of sets. Here in R3, you can do it in Rn, but I guess I should say we can do this really in Rn. Right, so H2 is just sort of this measure that we've cooked up, which does the job of measuring area in a higher dimensional space. You know, if we were in two dimensionals, if in R2, for instance, Lebesgue measure would do that job, but in higher dimensional spaces, you know, Lebesgue measure measures higher dimensional volumes, so you need this guy to measure the area of lower dimensional sets in the higher dimensional spaces. Right, and so, and in general, you know, we have H2, but we could also write, you know, HM for bigger M. So HM is something that I'll use later as well. This measures M dimensional volume. Okay, and then, so I wrote on S2, so when I say on S2 with this notation with the little L, really what I just mean is that when this thing measures a set A, I'm just taking the H2 measure of A intersected with the sphere. Okay, so the little L just means that I'm restricting myself to sets which are contained within the sphere. Okay, and so in this case, right, we're interested in the measure of balls. So here, you know, I've drawn a point here to the right here, X, and the intersection of a Euclidean ball, a radius R and R3 with the sphere is just one of these spherical caps. So if I write the distribution here, this is just going to be H2 of a ball of radius X R intersected with S2. Okay, which is, you know, the area of the cap there, which I won't prove here, but you can show relatively easily this is going to be equal to pi r squared if r is between 0 and 2, and 4 pi if r is greater than or equal to 2. Right, so when r is greater than or equal to 2, my ball envelops the entire sphere, and so it'll be constant at that point afterwards. Right, and so if I want to write this in a more a nice kind of way, I can write it like this. Right, using characteristic functions. Right, so this is what my distribution function looks like in this case. Okay, so these two examples have been nice, but their supports have been not discrete, I guess. So now we can get an example of one with discrete support. So here I'll write mu is the sum of a bunch of delta masses or point masses at the integers. Okay, so what does this mean? Well, delta m of A, this thing measures a set by its 1 if m is in A, and 0 otherwise. Okay, and so I should write in this case, you know, the support of mu is just the integers. Okay, so when I'm considering the distribution function here, I'm just considering balls centered at these points. So if I want to write f mu, well, okay, what happens at first? If I look at the, you know, the ball centered around 0, you know, at first I have radii which is sort of in here, so they're only containing the point 0. So, you know, at first my measure will just be 1. It'll be 1 if r is between 0 and 1. the next, I pick up more measure, at least the next time I pick up more measure is when my radius is greater than 1 in here, right? So my ball sort of contains these points 1 and -1. So the measure will be 3. If r is greater than 1, less than or equal to 2, right, and so on. I can keep on playing this game and just seeing that my balls will just pick up more measure when I get to these integer points. And so you do a little, just do a little thinking, and you can just write this in form as 1 plus 2 times the ceiling function of r minus 1, where the ceiling function here is really just taking the next greatest integer. So, if I write the ceiling function of 1.2, for instance, it's just 2. The ceiling function of 0.1 is 1. Okay, so this is an example of a uniformly distributed measure with discrete support. Okay, and then finally we have the example where I'll write H3 on C, where C is the set, a set which may be familiar to some of you guys. This is going to be X and R4, such that X4 squared Okay, so this is what's called the light cone, at least in special relativity. And here I've drawn it just in the case x3 equal to 0. This is one of the slices. It's, this cone in R3 that we're used to, at least. So this is, a 3-dimensional set, and it turns out that again, this is a fact that I won't prove here, but it turns out that the measure of a ball centered on any point in this cone, any point on the set intersected with it, is actually 4/3 pi r cubed. Okay, so the measure of any ball centered at any point in this thing scales like r cubed. Okay, so the point was just to give you guys some examples, some feeling of the sort of variety of measures that exist in this class. Okay. And so with that, we're going to move on to proving, using this condition to prove some simple sort of properties of these things. So one natural question that you can ask is how quickly can the measure of a ball, one of these kinds of measures, grow? Okay, and so the answer is given by, this first lemma. So if I fix 2 numbers s and r, s less than r, and mu is just any uniformly distributed measure, then I get this relationship between the distribution functions. So f mu of r is less than 5 to the n times the ratio r over s to the n times f mu of s. So really what this says is that, growth is polynomial. At most, right, where it's polynomial, it's r to the n. So it sort of grows at most like Lebesgue measure grows. Okay, and so what's a proof of this fact? Well, so I'll say fits x and r greater than 0, and fits what's called an s over 2 maximal net in VXR. Okay, so what's a maximal net? It's this thing I've drawn in the picture over to the right. It's basically this collection of points I'll call Z. So I'll call this net Z. Right, so here I've drawn is just z1 through 5. It's basically just a collection of points sitting in the ball, which are spaced at distance greater than or equal to s/2. And I fit as many of them in there as possible. So z is a maximal collection of points in BXR, the spacing at least s/2. Okay, just pack as many of these points in there as I can. Given the set, there are two sort of observations that you can immediately make. One is that the ball of radius star is contained in the union of the balls centered at each of these points of radius s/2. Okay, and sort of the easiest way to see this is just to think, okay, if this ball wasn't contained in this union, then there would exist some point in the in the ball not in that union. That means that there would exist some guy which is far away from all of the z's. It's at least s/2 away from the z's. And then I could add that guy into my net and still have a net and make a bigger one. Right, but I chose this net to be maximal. So that's a contradiction. That's point 1. And point 2 I can write is that the union over z and z of the balls of radius s/4 is contained in the ball of radius 5r/4, and this is a disjoint union. Okay, so the reason the union on the left is disjoint is just because of the spacing condition, right? All of these balls are far away from each other, so that if I take the balls of radius s/4, those things don't intersect, right? So if I draw, a ball of radius s/4, these guys aren't intersecting, and these are contained in the ball of radius 5r/4 around x, just because the possibility that I have points on the edge like z5 over here, I need to extend my radius a little bit there. Okay, so given these two conditions, we can use condition 2 to get a bound on the number of points in my net. So really, I have this disjoint union contained in my bigger ball. So this implies that I can write the volume for z and z, the bz s/4 is less than or equal to the volume dx 5r/4. Right, and then here, the volume of all my balls on the left side are the same. So really, this is just the cardinality of my net, the points there, times omega n s/4 to the n. It's less than the volume of the guy on the right. And rearranging this inequality, I get the cardinality of z (5 to the n r over s to the n). Right, so this gives me a bound in the number of points. And then here, I can use condition 1 to apply sort of mu, the uniformly distributed measure I'm interested in, to both sides of condition 1, and I can get the mu dx r is less than or equal to the sum of bz z s over 2, right, is equal to cardinality of z, all right, less than f mu of s, which is less than or equal to 5 to the n r over s to the n f mu of s. And so that finishes the proof. Okay, so really the fact that we have a uniformly distributed measure in Rn here was important, right? We use the geometry of Rn to get a bound here on the number of points in this net. And that ended up giving us that this measure can't grow faster than Lebesgue measure can, at least up to constant, right? Okay, so that's that statement. And then the second thing that we're going to need is this radial integration lemma. So if mu is uniformly distributed, and I choose 2 points x and y in the support of mu, then for any number s greater than 0, these two integrals are equal to each other, right? So what's the intuition for what's happening here? Really, I can just think of the integral on the left as, placing a Gaussian bump, right? This function e to the minus s, e minus x squared, is just, the PDF of the normal distribution, right? So it just looks, the graph of this thing just looks like a bump. On the left-hand side, I have a bump situated above x. On the right-hand side, I have a bump situated above y. So this lemma is really just saying that the area under each of these bumps is the same, right? And the reason I can conclude that is because my measure is uniformly distributed, the measure of balls around x sort of look the same as the balls around y. And we're going to see that we're going to be able to write each of these integrals as an integral of measure of balls, actually. Right, and so how do we see that? Well, I'll rewrite the integral on the right-hand side above here. I can just use the fundamental theorem of calculus to write it like this. So dt d mu of z. Right, and so by Fubini, this thing is really a product integral. It's a product integral that we're writing over points z comma t such that t is between 0 and e to the minus s z minus x squared. Right, so I'm integrating over sort of these pairs of points. So when I right, so this is sort of the perspective with respect to t, right? Because I'm writing t is less than this thing. Well, I can sort of switch this around, and I can think of this as pairs going the other way. And this time solving for, if I solve this thing for z minus x, let me see, I can actually, I'll just write it down instead of doing out all the calculations, but I can, this thing is equivalently just z minus x is square root of log 1 over t over s. Okay, so this is just solving this thing for z minus x. And so when I switch the order of integration here, really I'm integrating over, I'm fixing some t, and then I'm integrating over z such that this is true. So z such that z minus x log 1 over t over s d mu dz. Right, and so this guy is really the integral. And this set really is a ball, right? It's a ball around x. Dx square root of log 1 over t over s dt. right? But since my measure is uniformly distributed, try this in terms of the distribution function. Right, and so the point is that this is just the same around any point in the support. Right, so this is independent of the point x that I chose. I can write this in terms of y, and so on, and also using the growth lemma that I proved above, I can really just write this as f mu of 1 less than or equal to 5 to the n square root of log this thing to the power n. Right, and so I just need that to show that this thing actually converges to some finite number. Right, so the fact that my measure can't grow, any faster than some polynomial means that this exponential converge.
Jared, I have a question.
Yeah.
Does Lemma 1 only work for Lebesgue measure, or is it any uniformly distributed measure?
Lemma 1 works for any uniformly distributed measure. Right, so Lemma 1 is about here this distribution function for mu, where mu is any uniformly distributed measure.
So I think in the proof that you showed, we used the fact that the volume of a ball is like Wn and then something to the power of n, right? Isn't that only for Lebesgue measure?
Yeah. So this line right here, I'm using Lebesgue measure. But that only comes into play in order to prove the fact that the cardinality of a maximal net is bounded above.
Oh, okay.
So so I'm really what I'm using is the geometry of Rn. The fact that I can only fit so many balls of a smaller size into a ball of a larger size. Does that make sense?
Cool. Yeah.
All right. Okay, so that's a proof of this radial integration thing, the fact that this integral is going to be the same for any, if I stick a point x and a point y, which are both in the support, it's the same for any 2 points. Okay, and so actually, is there a question?
Yeah, can you show the proof of lemma 2 again?
Yeah.
So it's just still sinking into me because I'm looking at the last line where we're bounding it above, but we're saying that they're equal for any 2 points. But I suppose the line above that, we have this integral and there's no x or y. So that.
Yeah.
So
I kind of missed.
It comes.
Yeah, sorry, I did kind of mess that up because I kind of combined that with the proof that this thing is finite. But yeah, so to prove this thing is independent, I would really just write here, forgetting the last part, then as this integral y around x or y.
Yeah. Okay.
Right, and then I can go backwards in the other direction.
Yeah, it looks good.
Does that make sense? Okay.
Mm-hmm.
Okay, and so using that, we can actually prove sort of this lemma 3, which is we can characterize the support in a certain way. So just looking at the statement, if I fix x0 to be some point in the support of the measure, and I take just x to be any point in Rn, and s, this parameter greater than 0, I define this function capital F of x and s to just be the difference of the two integrals that I wrote above. Okay, but the difference here is that I'm allowing this x guy to be any point in Rn rather than a point in the support. Right, so the statement that I just proved above was that if x was also a point in the support, then this thing would be 0. here I'm allowing x to be an arbitrary point. Okay, and so given the definition of this function, the statement of the lemma is that x is in the support of my measure if and only if this function vanishes for all s greater than 0, for all values of this parameter. Okay, so for the proof, in the first direction, I'm assuming that x is a point in the support. I want to show this thing is 0 for all values s. Well, this is really just a restatement of lemma 2. Right, that was where we showed that two integrals them taking the difference of were equal to one another, which means that it's 0 for all s. Right, and so in the option, what am I doing? I'm saying that f is equal to 0 for all s, and I want to show that x is in the support. So the way we can do that really is to take the contrapositive. So assume x is not in the support of mu. We want to show f of xs is not equal to 0 for some s greater than 0. Okay, and in fact, what we're going to end up doing is showing that f of xs is less than 0 at some point. Okay, so below here, I've sort of drawn a picture of an intuitive reason of why this should be the case. So again, this integral on the left-hand side is sort of, it's a Gaussian bump centered around my point x. In this case, if we're assuming that x isn't in the support, so x not in the support of mu implies there exists, some epsilon greater than 0 such that mu of this ball is equal to 0. Okay, so and I've drawn that sort of down here on the left in red to show that mu doesn't assign any measure to this ball around x. And so if I think about what this means for the integral above, right, this integral on the left is the area under this Gaussian bump centered around x. This means that the part of the bump around its center isn't contributing anything to the integral. Right, and so if I make s really, really, really large, that means this bump is getting sharper and sharper and sharper around x. And more of the measure, the volume under the, this bump is being concentrated in a region which isn't contributing to the integral at all. Right, and so that's what's happening with the left-hand integral, and then the right-hand integral, it's this bump centered around this point x0, which is in the support. And so, all of the bump is always contributing to the integral. I'm taking all of the measure all the time. Right, and so eventually if I take s large enough, this picture is true, and the thing on the right has to be greater than the thing on the left, which means the integral on the right is greater than the integral on the left, and so this f of x comma s is going to be less than 0 for large s. Okay, so that's sort of an intuitive a picture of what things are happening. And down here, I'll go into a little more depth. So the way we kind of prove these things generally is using estimates involving annuli. So I can write this here is my left-hand integral above. You take this thing and I can write it as the sum from j equals 1 to infinity of the integral over here, right? So I'm taking the integral and I'm splitting it up into, an integral over first this annulus, and then second over the next guy, and so on. Right? And so I want to bound this guy above. So on each of these annuli, this function e to the minus s to this power is decreasing as I go further out. So that means on this annulus, it takes its largest value on this part, on the inner sort of part. So I can bound this guy above by e to the minus s k epsilon squared. I can just take this to be constant on this annulus, and I can take the measure here. Okay, and if I write this out, write this in there as the distribution function, right? Because mu is uniformly distributed. Okay, where actually I also used the growth lemma here as well. Okay, so this allows me to bound the integral on the left above, and then I want to bound the integral on the right below by something. So right. Okay, so this integral over Rn. I found this guy below. Well, really, I can just take, just look at the inside part. So this time, because all the measures concentrated around my point at 0, I can really just look at only at this inner part. So this will be greater than or equal to the integral of b of x epsilon over 2 I'm just looking at the inside part, and then on the inside part, my function is going to be greater than or equal to, the value it is on the edge. And the value it is on the edge is e to the minus s epsilon over 2 squared mu. It should be at 0. Right, which is just equal to e to the minus s epsilon over 2 squared. Like that. Okay, so to show that, the guy on the left is eventually smaller than the guy on the right, I can look at sort of quotient of these two quantities. And I can use the two estimates that I just proved. So less than or equal to, right, the guy above, or less than or equal to here. Whoops, don't need that. Right, so that was my upper bound for the first upper bound that I wrote, and then I bounded the guy below from below, so that I can put on the bottom u minus s 1 squared over 4. Epsilon over 2. So if I just divide these things out, you get epsilon squared minus epsilon squared over 4. Oops, e to that. K plus 1 to the n. Okay, and then as s goes to infinity, this thing is going to 0, right? Because I have e to some negative exponent here. So as I take s to infinity, this thing is decreasing exponentially. Right, and so what this shows really is just that I take s large enough, eventually this guy on the top is smaller than the guy on the bottom. Okay, so since the guy on the top is smaller than the guy on the bottom, remember what we wanted to prove was that this integral f x comma s is less than 0 at some point. So what we proved was that the integral on the left was eventually less than the integral on the right. And so this thing is less than 0 eventually. And it's less than 0 when this point x is not in the support. And so by doing that, we've proven that the support characterization lemma, we've proven that x is in the support if and only if this function f is 0 for all s. Okay. Okay, so with that, we can finally get a little bit of a payoff. So we've proven this characterization of the support. And so now we come to this theorem. So if mu is a uniformly distributed measure in Rn, the support of mu is actually an analytic variety. Okay, so it's the 0 set of some real analytic function. Okay, and so how can we do this? Well, we can actually explicitly construct an analytic function which is the 0 set of, whose 0 set characterizes the support. Okay, so I'm just taking this function f that we were talking about before. Okay, and we're going to set the function h of x to be the integral from 1 to infinity of e to the minus s squared f quantity squared ds. Okay, so this function h of x is equal to 0. What? It's equal to 0 if and only if, right, I'm integrating a positive function, if and only if f of x comma s is equal to 0 for almost all s greater than 0, right? But we just showed in the last thing that this is if and only if f of x s is equal to 0 for all s greater than 0. Right, because the proof of the last thing showed that if it was at some point not equal to 0, then if I just take s large enough for all large s, it'll be not equal to 0 as well. Okay, so we've proven this, and then the content of the last lemma was that this last condition is actually equivalent to x being in the support of mu. Okay, so we've shown that the support of mu is actually equal to the 0 set of this function h. Okay, and so now we need to show h is analytic. So in order to do that, really we're going to define a complex extension. So what we can do is we can define h tilde of x to be a similar sort of thing, this integral. And then integrating over Rn e to the minus s zi minus xi uh, 0 I. Okay, where in this case, h is some point in Cn. Okay, so all I've done is I've said that, you know, these xi's can now be complex numbers, whereas before they were just real numbers. Okay, and so one can show that H is actually holomorphic. Okay, the proof basically is you just write down the definition of the derivative, and then you have to show that this thing exists by doing, you know, some different dominated convergence arguments and stuff like that, but it's not too hard. And so once we've shown that this thing is holomorphic, it has a power series expansion. And that power series, when you restrict to these xi being real numbers, power series for my function h. So that shows that, you know, h locally has this power series, which means that it's real analytic. Okay, so that implies power series for h tilde. Okay. So we've just shown that the support of mu is always a real analytic variety by explicitly constructing this function h, of which the support is the zero set. Okay, and so that's a really nice theorem. It gives us a lot of information about, you know, the form that these measures can take. And specifically, it gives us information by this other proposition that I'm going to state, but won't prove because it's really hard, and I don't understand the proof. So it's this sort of stratification proposition. So if I just let Z be any analytic variety, so this is a statement I should say about the structure of analytic varieties in general. So if Z is any analytic variety, then for some integer less than n, I can write Z as sort of this union over these ZKs, where each ZK is actually an analytic submanifold of Rn. Okay, so, you know, an analytic manifold is stronger than a smooth manifold. So in particular, these things are smooth. So it's this union of sort of these lower, you have this top dimensional manifold, and then you have all these lower dimensional manifolds. And sort of furthermore, this thing at the bottom here is just saying that sort of the stratified part is that if I take Zi, the closure of this guy contains all of the lower dimensional manifolds. Okay, so the lower dimensional manifolds are kind of filling in the holes and the edges of the upper dimensional guys. Okay, so this is a really nice structure theorem about the form that these things can take. And so a corollary that I won't prove, but I'll just state of what this means for uniformly distributed measures is that, you know, if I assume the support of mu here is this union from k equals 0 to m of these zk's, then really mu is just measuring the volume of this top dimensional manifold. Okay, so mu really, all mu cares about is this top dimensional guy, and it's actually just a constant times the measurement of volume on here. Okay, where this constant is given by sort of the limit of my distribution function with respect to the m-dimensional volume. Okay. So I guess the point of this last part is actually just that you know, if I want to write here the measure of mu of A is just equal to this guy. Right, on the left-hand side, I have mu, and then on the right-hand side, I have this hm of A intersect Zm. This thing on the right is really just a function of the geometry of the support, right? The only part of involving mu on the side is Zm. Right, so really it's just saying that these uniformly distributed measures, all they can do is they can measure the volume of manifolds. And sort of the geometry of these manifolds tell the entire story. Okay. And so with that, we can look at sort of a nice special case in this theorem 2. So if we restrict to mu having compact support, we can actually prove that the support of mu is not only an analytic variety, but it's an algebraic variety. Okay, so if we look at this proof, so again, I'm writing down my function f here. It's the difference of these integrals. So remember, I'm assuming here that the support of mu is compact. Right, so if I take these exponentials, I can write this thing as the integral over Rn. Exponentials have Taylor series expansions, right? So I can write this is the sum from k equals 0 to infinity minus s to the k over k factorial. I'm going to write it like this. 2k. All right, so that's just expanding using the Taylor series. And then, so the fact here that the support of mu is compact implies that these Taylor series converge uniformly for z. Right, since I'm only considering z here, z in the support of mu. So these functions that I'm integrating here, the Taylor series converge uniformly to them. So I can interchange these limits. I can write this integral over r to the n. Okay, so now the sum is on the outside and my integral is on the inside. And remember that what we just proved when one of the lemmas was that x is in the support of mu if and only if this guy is 0 for all s greater than 0. And so if I set this guy equal to 0, what does that mean? I have this Taylor series expansion in terms of s, and this thing has to be 0 for all values of s. That can only be the case if the coefficients are 0, just dead 0 all the time. Right, so this implies that the integral over Rn is z minus x to the k, z minus x 0, z minus x 0, the k d mu. It's just dead equal to 0. And this is dead equal to 0 for all x in the support of mu. And this is for all k 0 to infinity. Okay, but if you stare at this a little while and you look at it, really, for each k, this is a polynomial in x. Right, if you sort of expand these inner products, and then you integrate, I get sort of coefficients which are integrals over z, and it's a polynomial in x, really, so I can define pk of x to be this guy. right? And so this implies that x is in the support of mu if and only if x is in the intersection of the zero sets of all these polynomials. Okay, and so that proves that the support of mu is actually an algebraic variety.
Jared,
Mhm.
can you say something again about how we use mu having compact support to show that this series converges uniformly and then switching the integral in the series?
Yeah, so so that step was right here, I think. Right, so we used right, this is a Taylor series that looks like e to the minus s to the k over k factorial times say some quantity, right?
Mhm.
So the point is that if I assume that mu has compact support, then this quantity is bounded above by like, you know, r to the k or something. Just where r
I
is
think
some
I
big
see it.
number. Yeah.
Okay.
I did that. I kind of glossed over that. You're right, but that's where the assumption comes in, proving that this integrand is uniformly bounded by some big constant.
Yeah. Okay, thanks.
Yep. And then I see that my time is coming to an end, so maybe I'll just say this last thing. So a nice corollary of this is that if mu is a uniformly distributed measure in Rn, and I have compact support, then I can actually show that the support of mu is contained in some n-1 dimensional sphere. Okay, and so I'll just say in words, the way that I do that is, right, I have these PKs that I've defined that I actually look at P1. And it turns out that if I write out what it means, you know, if I just plug in k equals 1 above in my expression for PK, and I write out what that means, you can show that all x that satisfy this actually have to be in the support of some sphere. And actually in the support of the sphere centered around the center of mass of my measure. Okay, so that's a really nice result that implies a lot of other nice things, but I guess I'll end there. Maybe you can take some questions.
All right. Thanks very much, Jared. Are there any questions?
Yeah, I had a question about, I guess, the relationship between these algebraic and analytic varieties. So is there any sort of like partial converse to that theorem 2 you're talking about? Like, can we go the other way in any sort of cases?
So if like, so given some kind of algebraic variety, can I construct some kind of like uniformly distributed measure on it?
Yeah.
Is that? Yeah, I really don't know. To be honest, I don't know anything about algebraic varieties at all. So
Okay.
maybe an algebraic geometer would be better equipped to even entertain the answer to that question. Yeah, I think that's a very interesting question, but the answer is I don't know. I have no idea.
Wait, what was the question again?
Question is basically, is there any kind of result like, you know, given an algebraic variety, do I have a chance of constructing a uniformly distributed measure on it?
Yeah.
Yeah.
If the variety is singular, say, I don't know, like 2 lines, will there be like a problem in the intersection?
Do you mean in general? Or I guess what's the context?
In say R2. for example?
Well, usually there is, but actually sort of, if you look back at the examples, this last example is one where I have a singularity right here at the origin, but it works out. So in 2 dimensions, it might be the case that, well, yeah, actually, well, okay, it depends for some measures, but this is a case where sitting in R4, it actually works out that the singularity, the measure around this place actually is still good.
I think for Willie's example, if you have length measure on this x, it's bad because if you center at the x point, it'll grow faster than on one away from the x point. So
Exactly. Yeah.
Yeah.
But yeah, this example that Jared has up is like magic.
Yeah.
Jared, do you know that your definition of uniformly distributed said there exists this FR, right? So if you're given an FR, can you construct a measure that is uniformly distributed?
I think in general, the answer is no. I think that there's some work on this, but it's hard. I think Price did some stuff with this, if you know who he is, but in this like sort of big magical paper. But I have not studied this too much. I think the answer is no, and there are some conditions you can write down for what it has to be, but yeah.
Right.
But there's
Any
still,
other questions?
Yeah.
Sorry.
That's okay. There's still, well, I mean, a whole ton not known.
Sorry.
Yeah, go ahead.
I have a question. I was wondering if you could tell us about the classification of measures in R and R2.
Right, yeah. I can maybe just say really quickly for, right, so first thing I wrote here is the classification in R. So if V is uniformly distributed, there are 3 sort of cases you look at. The first case is that the support is compact and discrete. And in this case, you just have, a mass. The first case is that you have 2 masses on the real line somewhere. The second case, you just have 1 mass. Okay, so that's not very interesting. The second case of this theorem is that the support is unbounded and if it's discrete and unbounded, then basically you have this picture above where you have a mass at the point AN, you have a mass some distance apart, and then that picture sort of repeats. So you're allowed to have 2 distances that alternate between points. Okay. And then the final case is just that you have Lebesgue measure in the real line. So that's all one-dimensional uniformly distributed measures. And then in R2, if you have compact support, we can classify these guys. And basically, the way you do this is so you know that from the previous result that the support has to be contained in some circle. And basically, you can show that you can take the one-dimensional result, you can sort of unravel the circle onto a line, and use that to prove this result in 2 dimensions. So the first case is that the support is sort of the whole circle, and it's just length measure on the circle. The second case is that I have the circle, and I just take a regular polygon on the circle, right? And I put point masses at each of the vertices. And then the final case, right, is that I have some circle. I have a regular polygon, but I'm also allowed to have another regular polygon sort of right next to my other guy. Okay, so they sort of come in pairs like that.
And I don't know, I think I missed a little bit what you said. So this circle, it can be like the real line, or like,
well,
the case for the one-dimensional also fits in R2. That would work, right? Or
yeah. Well, what I just meant to say was that, so a sketch of the proof would be like I have the circle. I know the support. Right, if I have mu as a uniformly distributed measure, the support of mu is contained in some circle somewhere. And so if I take a point centered, or yeah.
Because it's compact, I mean, then we're getting rid of like basically everything but the first case in the previous theorem. Okay, never mind.
Yeah.
Right. Cool. Any other questions? If not, then I guess that's it. Thanks very much, Jared.
Thank you.